Welcome to the fractional calculus seminar. It has been a pleasure to host the seminar series. Today we will have the last two talks for the seminar series for the year 2024, and we have Professor Wang, who's a professor at University of South Carolina. His research interest includes numerical analysis and scientific computing in porous medium flow and fractional problems. He has more than 200 publications on journals such as SIME Journal of Scientific Computing, SIME Journal of Numerical Analysis, SIME Journal of Control and Optimization, Multi-Scale Modeling Simulations, and etc. We are very happy to have you, Professor. You may please begin your talk.
Thank you. So first, I would like to thank Pavan and Arran for the invitation and for organizing this wonderful seminar series to provide this platform for people around the world working on fractional and non-local problems. So today I'm going to talk about the variable order or variable exponent fractional problems, and primarily on the modeling, analysis, and the simulation. So first, I would like to acknowledge the collaborator, Dr. Xiangcheng Zheng. Okay, this presentation is largely based on our collaborative works and also the recent work of his group. And and also I would acknowledge the support of the funding agencies. Okay, so I will start to expose the modeling using fractional PDEs, and we will first recall the normal diffusion. Okay, and if we recall that how the faking diffusion equation was derived, right? Recall that the diffusion, of course, is arise from the random movements of particles, right? And essentially, we know it's from high concentration to the low concentration. And of course, the first model was proposed by Fick, right, in 1855, when he was investigating the movement of neutrons through membranes, right? And it's later it's Einstein and Carl Pearson, right? They started this diffusion problem, okay, from the first principles. Einstein started from the first principles to study the collision of particles, right, and derived diffusion equation from that point of view. While Carl Pearson actually modeled diffusion via this random walk, right, and he was asking the question, right, if one person and it's just move a fixed distance, okay, in arbitrary angle. If he continues this movement, with a fixed distance but arbitrary angle for many steps, okay, where he will end up with, right? The reason he was asking this question is that he was studying how mosquito spread malaria, right? And the interesting thing is that although Einstein studied the problem for a microscopic scale, while Pearson modeled this problem from a microscopic scale, okay, actually their assumptions are the same. Okay, essentially, their common assumption is what? The underlying independent and identically distributed particle jumps must have a finite mean free path and a finite mean waiting time. Okay, under these assumptions, the central limit theorem will ensure that the normalized partial sum of the identically distributed and independent particle jumps converge to a Brownian motion. Right? If we look at the probability density of this Brownian motion is actually its Gaussian, which serves as the fundamental solution of the Faking diffusion PDE. Okay, and in the modern point of view, so that will be the Fock-Planck equation of the Brownian motion, right? So this is the key. If we recall the study of the faking diffusion, right? This is actually the key conditions. The assumptions one and two are the key conditions: mean free path and mean waiting time. This is actually also very important, the crucial to the study of fractional PDEs. Now the natural question is, okay, what assumptions one and two means from a practical point of view, right? And theoretically, we know, mathematically, we know what that means. But from an application point of view, what's what they mean, right? If we think the assumptions of a finite mean free path and the mean waiting time, that actually implies what? Implies the medium must be very homogeneous, right? This was in fact studied by the hydrologist Jacob Beer in 1960s, right? He observed the solid plume will demonstrate Gaussian behavior. Okay, it's decay exponentially. Okay, when the solid transport take place in homogeneous aquifers. Okay, then uh, later, and people naturally extended the model to model transport in heterogeneous media, right? And the common practice, okay, is what? We're still using a frequent diffusion model, right? But introducing variable parameters, right? By adjusting these variable parameters, they try to model the transport in heterogeneous media. Then, and it is people realize that if you use the PDE to model transport in heterogeneous medium, okay, the conventional advection diffusion, right? They often yield and very rapidly varying diffusivity coefficients and tend to yield less accurate predictions on testing field data. Okay, and that puzzled people for a while. Okay, then and people realize what the field test of transport in heterogeneous aquifer actually and exhibits quite a different behavior. Instead of a Gaussian behavior as transport in homogeneous medium, the transport in heterogeneous media is often demonstrates highly skewed and parallel decay behavior. Okay, so this is explains why the variable coefficient integer order advection diffusion equation and does not necessarily doing a good job because fundamentally, mathematically, the variable coefficient advection diffusion equation means that people using a combination of exponentially decaying functions to capture a parallel decay function. Okay, we know this could yield less accurate predictions over a large parameter range, right? So that is explain when the integer order advection diffusion equation might face challenges. Okay, essentially, if when the model heterogeneous medium, the transport in heterogeneous medium. Okay, and why the question now is why fractional PDE may work in this time, right? If we look at how fractional PDE were derived, right, and they actually were derived and using like a continuous time random walk and stochastic analysis, right? And they were derived under what condition? Under the assumption that the PDF have a parallel decay tails. Okay, and so in this case, the solution of fractional PDE was the model, okay, was derived, okay, and was constructed so that this solution naturally uh, uh, behave this parallel decay. Okay, that's why it is explained. So they can better capture the behavior of transport in heterogeneous medium, right? And people, I mean, over the years, there are a huge amount of literature work, right, that shows that when fractional PDEs were used to model transport in heterogeneous medium, they tend to fit the training data with a smooth and almost constant, okay, diffusivity coefficients. Okay, so uh, this is the explains why fractional PDEs may provide a competitive modeling framework for transport in heterogeneous medium. So essentially, if the environment, the medium is heterogeneous, okay, fractional PDEs may provide a competitive modeling framework. Okay, now back to the assumptions of the one and the two. Remember, the classical faking diffusion model was derived under the assumptions of finite mean free path and finite mean waiting time, right? If the finite mean free path assumption was violated, okay, that means the particle will have long jumps. That will lead to what? If you have long jumps, that means that will lead to super diffusion, right? Consequently, in that case, space fractional PDE will occur. Okay. On the other hand, if the assumption two, the finite mean waiting time is violated, okay, in this case, that means the particle jumps have a longer waiting time, so they move slowly. So in this case, actually, this will lead to the subdiffusion process, or mathematically, that will lead to time fractional PD. Okay, so this is the we can see now, and what is the connection of fractional PDE with classical Ficken diffusion, and what kind of conditions, what kind of environment they will be needed. Okay, okay. Now we go back to now. Let's get back to this mathematical and numerical issue of the models. Okay, this is a standard time uh, fractional diffusion equation, right? And we know this equation was derived via the continuous time random walk. Okay, one good reference, an excellent reference will be the work of Mehta and Klafter, right? So, and in this case, okay, if we look at the uh, the solution, okay, the solution actually is given by equation two, okay, by this here, right? We have this solution in terms of Mehta Leffler functions, okay, and it we can see that this solution correctly demonstrate the parallel decay behavior. Okay, so this has been widely used. Okay, but what is the issue here? Okay, what is the issue here with this model? Okay, and so the limitation of this model is what? And people realize that this is about more than 10 years ago, right? Like by Sakamoto, Yamamoto, and Martin Stein, etc. Okay, so the issue they quickly realized that the solution of the time fraction PDE demonstrate initial weak singularity. Okay, the one. This is a widely used plot, right? And so and now people raise the question: this initial weak singularity behavior of solution, is that physically reasonable behavior, or is it due to the model issue of whatever? Okay, and later, and uh, this two-sigma model actually was introduced by hydrologists. Okay, in addition to the time fraction term, they also introduced a first order term. Okay, this is a two-sigma model. Okay, and from a modeling point of view, what this model means is this. Okay, it's a model the case during the transport of the contaminant of the solute. Part of them will be adsorbed to the porous medium, okay, and stay there for a while. And the other part will just go with the water, okay. So that's why they form this two phase here, okay. One is a phase flowing with the groundwater. One will stick to the porous medium, and it may get released later, okay. This K is a partition uh, constant that tells that 1 over 1 plus K portion of the total solute mass will flow with the water. K over 1 plus K portion of the total solute will become absorbed to the medium and will be released later. So this part is actually responsible for the subdiffusive effect. Okay, so this is the physical explanation. Okay, and now as we can see, so this is some of this mean square plot. Okay, this is in the um, log scale. Okay, and if we look at this plot here, okay, the uh, the uh, this curve here, okay, this curve, okay, that is just a line with slope zero point 0.3, and this one is a line with a slope 1. We used as a uh, reference, okay, and the first curve is this solid line. That is actually the solution of the Ficking diffusion equation. Okay, the solution of Ficking diffusion equation, if we look at the mean square displacement, okay, that actually had a slope 1. Okay, and if we look at the second curve, okay, the second curve is what? The second curve is the solution of the one term time fractional diffusion equation. Okay, just one term. Okay, so that if you look at this solution, the slope is zero point 0.3. That's like this one. Okay, and then the other three curves, 3, 4, 5, is actually all solutions of that two-term equation. So the curves 3, 4, 5 is a no this one is a solution of this equation, but depending on different values of this partition coefficient k. Okay. In fact, the curve three, okay, the curve three here is is what? That is for k equal to zero point zero 0.01. So roughly speaking, 99% of the solid flowing with the water, only 1%, about 1% of the solid was adsorbed to the porous medium. So you can see its solution is quite close to the Ficking diffusion. And you start to see a little bit deviation for larger time. Okay, so that that is as expected, right? And the curve four, okay, curve four is what? It's for k equal to one. K equal to one means what? Half of them is in flowing in water. Half of the solid is stick to uh, porous medium. Then this is actually show the interesting behavior. So you see the solution is what? Initial its slope is quite close to the Ficking diffusion equation. As time increase, okay, the slope of this curve converge to the solution of the subdiffusive equation, right? So that tells us the this two-scale model is actually demonstrate or capture the multi-scale behavior, the two-scale behavior of a physical process of a transition from a Ficking diffusion to a subdiffusive transport. Okay, the last curve, the curve 5, okay, has a similar, curve 5 correspond to what? Corresponding to k equal to 100. So that means most of the solid was absorbed to the porous medium, only about 1%, okay, flowing with the water. Okay, now you can see the behavior is very similar to the one-term model. But the question is what? The question is that the constant are different, right? The y intercept are different. Okay, what this tell us? Okay, what this tell us? Okay, if we go back to this plot, this actually can tell us a lot. Okay, this plot is similar to the left plot, except that we uh, we carefully choosing the initial condition to have a very small uh, support. Okay, what you see is that as time evolve, okay, the solution quickly uh, decrease, like the plot on the left. If you look at the time scale is actually very small, from 0 to 0.01. Okay, and on the other hand, and if we look at the red plot and the middle plot have the same scale. Okay, but this is the solution of the two-scale model. This is for this partition coefficient capital k equal to 100. So this is the solution of the two-term model. This is a solution of the single-term model. Okay, and and if you recall the plot, the mean square displacement plot we just showed. Okay, what this means that the uh, the reason is that that's the better to go back to the reason that they have the same slope, okay, and the same decaying behavior, but the constant difference. Constant is what? Is the variance, okay? The variance is large, means what? Means the base of the plume is large, right? If the base of the plume get large very quickly, okay, the mass conservation ensures that the area does not change. So the height must decrease very rapidly. That means what? That implies the fast decay in time are all the initial Wink singularity. While the two-term model is actually, you can see the solution is very smooth. Okay, the solution is very smooth. This demonstrates the mathematically, the two-term model gives and much better um, mathematical behavior, the regularity, while they actually capture the subdiffusive behavior of the problem. Okay, so that this mean square displacement basically shown that the two-term model provides a physically reasonable model. Okay, we will address this issue later. Okay, more. Okay, okay. So and then I mean, in other words, the single-term model is a good model outside of the initial time area. Okay, while the two-scale model gives uniformly accurate modeling from including the initial time, I mean, all the way to later time. Okay, yeah, and we talk about this. Okay, why variable order models? Okay, the reason is that the fractional model, okay, the fractional derivative actually closely related to the fractal dimension of a material through the so-called Hurst index. And in the book of Mirshat and Sakowski, and they actually demonstrate this in the stochastic sense. Okay, so in many applications, okay, like long-term vibration of viscoelastic structures, like oil reservoir simulation, like in groundwater contaminant transport, okay, and the structure of the medium might change, okay, and in vibration we can imagine, right? Long-term vibration will damage, eventually damage the structure of the material. The damage will cause the change of the fractal dimension. In oil, gas, oil reservoir, okay, like shale gas production, okay, they use hydrofracturing to damage, to break the geological formation to increase the porosity and the permeability. Okay, all these kind of process actually change the fractal dimension, and so the uh, the fractional order of the problem. Okay, similarly in other applications. Okay, the key is what? The key is that fractional and especially the variable order fractional model provide more physically relevant and mathematically and numerically very convenient, okay, the modeling tools. Okay, so that's what I mean. In summary here, right? The variable order fractional PDE offers a seamless modeling approach, right? So provides this flexibility by uh, by the change of the order, okay, they can naturally modeling the transition between local and the non-local dynamics, and among other choice and fine scale and cost scale behavior. Okay, and it's also offer a natural mechanism to eliminate the non-physical initial weak singularity of this constant order time fractional PD models. Okay, and we will show that. Okay, and they also offer a practical framework for constructing data-driven fractional differential operators. So it's a naturally can provide a framework or platform now to combine with the machine learning and the data-driven. Okay, so this is the flexibilities of the variable order models can provide. Okay. Okay, so this actually is also the plot. Okay, this is also plot to that mean square plot, but this is experiment, right? This shows what, and in fact, we can see many of these plots from different areas, so that what the mean square um, uh, displacement, the slope is not constant in general. Okay, the behavior is not constant, so that this naturally support the application, of variable order models. Okay, that said, okay, now let's go back to the mathematical analysis and numerical simulation, etc. Right? And here we talk about this variable order model. Okay, and this is again, as we said, we use this two sigma model here. Okay, and and different models can be used. This can be the computer, can be Riemann Loivel. Okay, and can be what even with this same variable order model, they actually can have a different kind of variable order models. Okay, and for example, if you look at this variable order model, okay, the key difference is what you see. The variable order here is dependent on time t. The time t is what is the upper limit of this integration. Okay, as time change, if your t varies, okay, then the order change on the entire interval, okay, change immediately. There is another types of a variable order model is what? This is the alpha depends on s. S is this integration variable, right? It's a and it's a depend on s but not on t. Okay, so this one will accommodate the change of the material in the evolution process. Okay, the other models can also be used. You can assume this. Some models assume that this can depend on both s and t. Some may assume this instead of t, they use t minus s, so that will be a translation invariant model. So we will not go to, we will just summarize some results in the literature. Okay, and we'll probably not go through too much detail due to the time limitation here. Okay, and in terms of this analysis, typically what we are doing is basically using the spectral analysis, right? And the idea that expand the solution by the eigenfunctions, and then reduce the solution of PDE as a sequence of ODEs, right? And ODEs then this essentially can use the analysis of integral equations, like integral equations with weakly singular kernels. Okay, and that is a general technique. Related techniques you can use energy estimate or semi-group analysis. Okay, I mean, as we said, due to the time constraint, we will not go through the detail here. Then I will show some results here. So this is the results of Xiangcheng and myself. Okay, and this results showed what? This showed that, for example, if for the computer variable order fractional diffusion equations, this will be the stability estimates. Okay, and if we uh, look at the same problem with the Riemann Louisville fractional PDEs. Okay, then we can see what? We can say that essentially the idea is what? Essentially is idea if the fractional order at zero equal to zero, okay, then the solution of Riemann Louisville solutions may have the same regularity as the computer. if the alpha zero is bigger than zero, okay, this actually the Louisville solution has one order less regularity, okay, and in this case, the computer does not have any constraint, any assumption on the alpha zero, right? Similarly, we can see that so this is the high order regularity of Riemann Louisville PDEs, okay, essentially if you want to get high order estimates, now we need to make more assumptions on the behavior of variable order at zero. Okay, essentially, the variable order at zero determines the regularity of the solution to the variable order fractional PDEs. Okay, and this is the one for computer. Okay, and I will not go back to this much because we have many of these kind of results. But the basic idea is what? Basic idea is under the same condition. Okay, computer fractional PDE has one order high regularity. Okay, the Riemann Louisville. Okay, in fact, we have this is a plot. Okay, the plot is what? So this is a solution. The first column is a solution of a computer fractional PD, variable order. Okay. The second column is a solution of its derivative. The third column is a solution of Riemann-Louisville. The first row is for alpha 0 is bigger than 0. The second row is for alpha 0 equals 0. As we see, roughly speaking, is what? The derivative, okay, the time derivative of the solution of a computer fractional PDE is about the same as the behavior of Riemann-Louisville PD, the solution itself. Okay, so that's actually support the analysis. Okay, okay. Then this that is previously that is for what? That is for the analysis of which PD. That's for solution of this one. That means this order depends on T. Okay. If this order depends on S, as you can see, the analysis gets harder, but the results actually gets better. So this is the one. This is called hidden memory. Okay, the hidden memory solution gets better is this. Okay, it essentially says that if we want to get high order regularity, we do not need to assume the condition of the derivatives of alpha at zero. Okay, the first order, second order, high order derivatives of variable order at zero. Okay, it's only if alpha zero equals zero suffice for high order estimates. So this one is for the hidden memory. That's the we call it the S dependence. That is for the this equation. So the variable order depends on S, depends on the integration variable, not on the upper limit of the integration. Okay. Okay. Then this is the discretization, and due to the time constraint, I will skip this part. It's basically saying that uh, we can, based on the regularity analysis, we can design the scheme accordingly without assuming, explicitly assume the regularity of the true solution, but only assuming the regularity of the data. Okay, so we can then prove the optimal order estimates. What this optimal order means? Okay, the optimal order sometimes means with respect to uniform partition, and sometimes with respect to a graded partition. For example, like we put this estimate of this variable order PD on uniform temporal partition. Okay, even this on uniform partition, independent of the value of alpha zero, even though we know that when alpha zero is a positive, is not zero, the solution, the second order derivative is actually unbounded, we will still be able to prove the uh, optimal order estimates, second order in space in terms of h. The first order is in terms of the number of time steps, right? Yeah. So then for Riemann-Louisville, and then we need to be careful. Okay, if alpha zero is bigger than zero, if we still use a uniform partition, we do not get an optimal order estimates. But if we use a graded mesh, we can still get optimal order in terms of number of time steps. Okay, if alpha zero equal to zero, okay, and even though on uniform partition, we can get optimal order. Okay, first order. Okay, and this is the numerical results. So I will skip that part. Okay, the reason is what? Now I want to basically now report the work of my collaborator Xiangcheng Zheng and his group. Okay, the the idea is this. Okay, the idea is that it over the years it had been people have been have these questions. It's a sort of an open problem. Is this? You said, well, with this two-order model, you can derive many good, I mean, analysis. Okay, derive many good analysis in terms of theoretical analysis, numerical approximation. Okay, is that possible? We can use one term model. Okay, I just use this variable order term. Okay, not use two term. Okay, the mathematically the first order time derivatives helps analysis, right? And can we just use this single term uh, model for convenience and also for mathematical uh, basically meet the challenge, right? And the key question we know immediately that without the first order time derivative, okay, the previous analysis we just talked about don't work. Okay, then indeed there are actually some yeah. Okay. Oh, sorry, okay, that's one question. Yes, someone has me. Oh, okay. Okay, so far, and there are some work in this direction, right? For example, uh, several category of work. The first category is what? We have a time fraction PDE, but the order can depend on space. Okay, spatially dependent variable like order. Okay, and another group, another class of work is what? After we transform after the fractional equation was transformed to the Laplace domain and allow the order to vary in the Laplace domain. Okay, there are some results in that direction. And thirdly is and if they allow the order to vary in time, like piecewise constant, okay, to uh, vary in time, and at each time step is constant. And the last group of work is basically the recent work of Xiangcheng Zheng. Okay, his study this variable order model. Okay, this first order model. Okay, and I will speed up a little bit. Okay, the one way what he did is basically using a convolution technique. Okay, and the idea that choose the constant kernel. Okay, this is the standard Abel type of kernel, right, for fractional PD, but constant order. If you take a convolution in this order, okay, with the variable order model, but his variable order model, this by the way, I want to mention, in this case, he studied the case of what? This variable order model is the what? Is the translation invariant. That means, well, we will see that here. So the model is here. Where the model? Let me see. Okay, okay. The model is like you see, this fractional variable order fractional derivative is a convolution of a kernel with the first order derivative. But this kernel is dependent on t, right? Once you do convolution, so this t becomes t minus s. So in this case, this corresponding to the case this order this order here is not t, not s. It's just t minus s. So this t minus is with the same with this t minus s. Okay, that is the work. Okay, was done in his new work recently. Okay, the new work recently. The idea like this: after doing the convolution, okay, he can write the convolution as this function gt and in because the thing like this is it's easy to see if this alpha t is a constant alpha, okay, then this g of t is actually one. Okay, g0 is one, okay, and g of t is one. Okay, g of t is one, and so this g of t can be considered as an approximate identity. Okay, approximate identity. In general, if the alpha is not a constant, okay, then and you can still show what, and the simple calculation can still show g of 0 is still 1. Okay, so this gave the uh, convenience to transform this model to what? This model to a two-term model. Okay, to a two-term model is one have the first order time derivative. Okay, but meanwhile, this will also have a Riemann-Liouville fractional derivative on the spatial term on the right-hand side term with what? With convolutional term with G prime. Okay, what the G prime was is G here. Okay, so the idea is what? The idea is that by doing this convolution, okay, this one term variable order term with this particular kernel is a convolution type of kernel. Okay, is that is transformed to a two-term model. Okay, this two-term model is in terms of Riemann-Liouville fractional derivative. Okay, once we transform this to a two-term model, then the classic, the previous preceding analysis can apply now, essentially doing this semi-group analysis, right? And I mean, taking the Laplace transform and this inverse transform, then this analysis works, okay? Because if you look at the transformation, is is what is this equation is transformed from our original equation. So the one term Abel PD model and the transformed two-term model are equivalent. So they share in the same solution. This is the key, right? This is the key. And now, in order to show the analysis of the one-term model, okay, so he can just analyze this two-term model. Okay, it's a different two-term model. Okay, by doing this, okay, he actually showed the following results. Okay, the results is what? That if the on the appropriate condition on the source term and the initial condition, okay, he can get the solution, the well-posedness of the problem of the transformed model and so the original model because they share the same solution, they're equivalent, right? And also for high order estimates. Okay, that is the result. Due to time constraint, I will not go through the detail here. And similarly, for no, in addition, if for the homogeneous right-hand side, a very smooth initial condition, okay, then this he can prove that the alpha zero can be determined by the following uh, formula. This is used to for what? This for the inverse problem. Okay, for the identification of the variable order. Okay, so that is a result related to that. Okay, and similarly, it can derive a numerical scheme is yeah, derive a numerical scheme. It's essentially similar idea, but without doing the numerical differentiation, but just taking this convolution. Okay, now without taking the first order derivative in time, we get an integral equation, and consequently, he can derive a numerical scheme here. And due to time constraint, I will skip this part. Okay, but yeah, I will skip this part. Okay, but this thing actually I want to emphasize this part. Okay, as I mentioned over the years, people have been asking, can a single term variable order fractional PDE diffusion PDE can be derived to uh, by uh, by adjusting the behavior of this variable order, we can get a single term fractional PDE that can replace the two-term model. Okay, and what Dr. Zheng and his group, okay, recently had a paper in this. This was studied for the other fractional PDE, as I just listed. That means the kernel, eventually the fractional derivative is a convolution. Okay, and then if you want this model to replace the two-term model, one would require the alpha zero must be one, right? At the initial time, the fractional order model should capture the first order behavior. The alpha zero should be one. And the key observation, one of the key observations in the paper is what? Let's say if we just consider the case of alpha is C1. Okay, do not have the C1, but let's say if alpha is C1, then the idea that we look at the kernel, okay, the kernel for this particular PD is actually the limit is equal to minus alpha prime zero. Okay, this means what? This means that actually the kernel in this case, okay, is no longer singular. It's not a singular kernel anymore, but it's a regular kernel. If it's a regular kernel, you have a convolution, okay, at t tends to 0, okay, that term, okay, and you cannot get a first order term out, okay, because the the kernel is regular. You have also an integration, okay, so that will not give a UT term, okay. So this observation showed what? This observation is essentially saying that at least at least in the context of this kernel, okay, it's it's no hope to find a single term variable order model that can replace the two-term model. Okay, that is because the the kernel will be regular and that term will degenerate. Okay, if that term will degenerate, the previous work of Martin Stein and his collaborator essentially show that then your initial condition and the boundary condition, whatever, must satisfy some consistency condition. Okay, if the consistency condition is not satisfied, so that's impossible. Okay, so this is the one point I want to emphasize. Okay, then and consequently, he just proposed an alternative two-term model. Okay, the two-term model is that now use a Riemann-Liouville variable order derivative, the same convolution type. Okay, and why he's proposing to use this model is that recall in the constant order case, how fractional PD was derived. Okay, this was in the work of Metzler and Cluster. Okay, the fractional PD was derived from a continuous time random walk. The first equation they get, the fractional equation they get, is actually equation 17. This Riemann-Liouville fractional derivative. Okay, from this equation, they get this field equation. They get this equation. This is in the constant order. Okay, in the constant order case, this equation and the other equation are equivalent. Okay, but in the variable order case, it's not. Okay, the variable order case is not. Okay, in the variable order case, what they showed is that okay, in this case, and if alpha zero, since they have the first order, now they assume alpha zero equal to zero. Okay, if alpha zero equal to zero, so this model at t tend to zero, this actually and behavior like a faking diffusion equation. So that's why they call it a local modification. Okay, the presence of this first order term in the model now eliminates the need to imposing constraints. Okay, now they do not need this constraints on the data. Okay, as they showed that this new total model also effectively capture the transition from Brownian motion to subdiffusion. Okay, this is the same behavior, similar behavior as the previous two-term model I just showed. Okay, and again in these results they showed this. Okay, the basic idea they showed is what this new model it seems initially this behave like faking diffusion, and the later time it's like this classical subdiffusion equations. Okay, so this is a new two-term model in the context of this translation invariant definition of the variable fractional derivative. Okay, so this is all I want to report, and thank you very much for your attention.
Thanks, Professor Wang, for the nice lecture. That was quite detailed analysis. For questions, please raise your hand. I'll call out your name as they appear on my screen. Vasily, do you have a question?
Yeah, maybe some just compliments. Thank you very much. Very nice talk. Enjoyed it. And just wanted to mention that maybe you didn't have a chance to look. I have a couple of papers on this variable.
Oh, sure. I mean, that'd be great. Yeah.
Yeah, with the direct derivation from continuous time random walk, all this.
Okay, that's great. No, definitely. I'm very interested in that. In fact, that okay. Oh, Vasily. Okay, sure. Yeah.
Yeah, there is a derivation with the even infinite dimensional version.
Oh, okay. Actually, I'm very
kinetic
interested in that.
equation, fractional.
Yeah,
Yeah.
I'm very interested in that. And could you please send me a copy of your paper?
Yeah, sure.
Okay,
I will be
excellent.
happy to.
Okay.
Thank you.
Thank you. Right.
Thank
Really
you.
appreciate it. Yeah.
Do we have any more questions or comments? You may unmute your mic.
I have one general question.
Sure. Yeah.
Please.
Thank you.
Yeah. Thank you for a really interesting subject and also very clear, and we got interesting information on those models. My question is, you in the model, one model with
Okay.
one term,
Okay.
fractional time, convert to two-term model
Yeah.
under some condition.
Yes.
So I have one question. Is this legitimate to ask? One can look at, then in this case, can one ask, look at the model number 7
Oh,
as,
okay.
as the result of one term model? It looks like inverse problem.
Let me show this again.
Model 7, page 26.
Right. So you said that this actually this is the work of page 26, right?
Yes, equation model 7.
Okay. Yes.
Yeah.
Right. So,
So my question, can you look at this model now, because we present already one model with one term, a single term, and was converted to two
yes.
term,
Yeah.
right? So
Right.
my question, if I look at the cipher, can I think about this as the result of one single term model?
It's this actually this
Yeah.
work this work of Xiangcheng. Okay, and here this is the reference. My
Yes.
understanding is that in the variable order case, this the computer version and the two-term model is not equivalent, right?
Okay.
Yeah,
Okay.
in constant order case they're equivalent. In
Yes.
variable order case they are not equivalent. That's that thing is that's the one of the key
Okay.
the results in this paper basically show that it will be not possible to use this one-term model in
Okay.
at least in this case, in this convolutional case,
I see.
and with to replace the two-term model. The two-term model works, but it's this one not. Right?
Okay. If we consider that the same from 7, why people they don't study the fractional Laplacian, the fractional in the position x? Because fractional
Oh,
position in the aquifer or something, it has some physical meaning.
oh, sure. They can study fractional Laplacian. In fact, the Xiangcheng and I had one paper that was fractional in Laplacian. And that was a spectral fractional Laplacian. People also studied the fractional Laplacian. In this talk, we actually only talk about the temporal fractional. Okay, in terms of spatial fractional, is a also is a there are some other generalization in the sense is what the fractional term, okay, it's cursive but not symmetric, not like fractional Laplacian. This can occur in post medium, whatever. The
Yes.
reason that if you think in applications, okay,
Yes.
this non-local in space not necessarily symmetric. Okay, in
Exactly.
fact, the order for different directions, the
Yeah.
order, this not only depend, this can change in different directions.
Yes.
This is the work of early work of Vince Irvin in
Okay.
2007, I think. Is also in work of Mark Meerschaert.
Yeah.
In Vince Irvin's paper, he actually did a very rigorous analysis, but that was done only true for constant order. And in our work 10 years ago, we gave negative results, showed what? If the variable, if the coefficient is not constant, like say just a piecewise
Yeah.
constant,
I see.
then the fractional model will lose coercivity.
I see. Thank you so much.
Yeah.
Thank
Thank
you.
you.
Are there any more questions? You can unmute your mic. Okay, there seems none. I just have one trivial question. So in your two-term model,
Yes.
you had a fractional derivative in time, which
Yes.
takes the argument as the Laplacian. So that Laplacian was in space, or
Yes.
okay? Are these
So
equations?
this, in fact, I mean, I did not talk about here. In fact, in some other application, if you think about the modeling viscoelastic material, the vibration of viscoelastic material, in that case, it's naturally the time fractional derivative and the space derivative are coupled together. It's from a physical derivation. It's not a mathematical technique.
I see.
Yeah.
That is quite nice to see
Yeah.
about it. Actually, recently I also derived fraction Navier-Stokes from first principles, and
Mhm.
I had a similar operator. So the
Okay.
fractional in time, the
Mhm.
argument was a transport term, where the transport term had a fractional in space. So
Oh, okay. Yeah. So
so
yeah,
so it
that is
was
great. Yeah.
yeah. So that those are my equations that I derived. I have my talk here within the seminar series, but
Okay. Sure.
I'm yet to write the manuscript, but soon enough. But yeah, I was actually quite puzzled by the equations that I had. I was like, okay, but it's nice to see that.
Sure.
there are other applications for that too.
Definitely, we need to keep in touch, right? To talk about
Yeah,
this.
sure.
Okay,
Looking forward to it. Yeah.
Yeah.
So, are there any more questions or any remarks, comments? Okay, probably no. So, I believe this is a good point to stop this talk here.
Okay,
Again,
great.
Professor
Yeah.
Wang, thank you
Yeah.
very much for the talk.
Thank you.